Okay, so this is the answer that we've obtained for the energy of the vacuum. It's divergent. We've got a sum over k. So in particular, the very, very large momentum modes, which correspond to very small wavelengths, give us a divergence, an infinity. Now, how should we think about this infinity? How should we interpret it? Well, in this particular quantity, this infinity is not very important. And it's no big deal. And I'm going to try to argue now that it's no big deal. This is not always the case. We'll find infinities appearing in other places where we will really have to interpret it and have to make sense of it. But the infinity in the vacuum energy isn't a big deal. Well, firstly, in classical physics, we don't typically care about the actual value of the energy. It's only differences in energy that are important. So think about forces. Forces are given by the gradient of a potential. You can add a constant to the potential without changing any force. So it just doesn't matter what the zero of energy is. You can add or subtract a constant energy to your Hamiltonian without changing the dynamics at all, okay? And in quantum mechanics, it's like that too. Remember how the equation of motion is given to you? It's Heisenberg's equation. So that's the time derivative of an operator is related to a commutator of the operator with the Hamiltonian. So if you choose to add a constant to the Hamiltonian, well, it just doesn't matter. Okay, so the value of the energy, the absolute value of the energy really doesn't matter. Now, of course, there is an exception to that, a famous exception that you, in fact, may know of, and that exception is in Einstein's theory of general relativity. In Einstein's theory of general relativity, the actual value of the energy does matter, and it enters into the Einstein equations, and it can have an observable effect. So one way that you will have heard this being discussed is when people talk about the dark energy. The dark energy has a natural interpretation as the energy of the vacuum, and this certainly is observable. It's observed in generating the expansion of the universe. So when we measure how fast the universe is expanding, we are actually measuring the dark energy, the vacuum energy. And now you may have a thought, as any good physicist would, why don't we look at all of the fields that there are in nature? Why don't we add up the 1/2 h bar omegas for each of the oscillators of the different fields that we have in nature? And let's see what value we get for the vacuum energy. Can we explain the dark energy? Great idea, good intuition, good insight. But I'm afraid your calculation doesn't work. If you do work out what is the vacuum energy, it comes out way too big, much bigger than what we observe. And when I say way too big, I don't mean like big off by an addition of 100 or even off by multiplication by 100. In fact, your answer is 120 orders of magnitude too large, okay? So we don't really understand how to get the dark energy. Because we don't understand it, I'm certainly not going to explain it. But the first reason why this divergence is no big deal is it affects what we call the zero of the energy. And that's inconsequential. At least when you're not dealing with gravity, it's completely unobservable. And for example, if you were calculating your Heisenberg equations of motion, it really doesn't matter if you add a constant to the Hamiltonian. Now, there's another reason why this isn't important, and it's because it's related to an ordering ambiguity. In the classical theory, P times X is the same as X times P, so we can write down either. When you come to the quantum theory, there's always an ambiguity in the order with which you should write your operators. Now, notice something, okay? I've given you the Hamiltonian at the top of the page here. And where did our answer come from? Well, the answer came from the second term. That second term is what gave us a contribution to the vacuum energy. The first term, you'll remember, gave us 0. And that's because the annihilation operator, alpha of k, acting on the vacuum is 0. So the reason why we got something non-zero was because we had alpha alpha dagger and not alpha dagger alpha. So this non-zero vacuum energy is just related to how we've ordered the operators. If we had ordered the operators in a different way, we would have gotten zero. So this infinity is really associated with an operator ordering ambiguity. So we don't think that it is very meaningful. But what it does suggest is perhaps there's an interesting ordering for the operators that we could consider. And this ordering is called normal ordering. Okay, and I'd like to define what it is now. So normal ordering. I'm going to define it just using an example. It's a simple idea, so you'll definitely get it. Let's imagine I've got a product of 4 operators. Maybe I've got alpha of K1. I've got alpha dagger of K2. I've got alpha of K3. I've got alpha dagger of K4. So I've just got a product of 4 operators, a mix between creation and annihilation operators. When I want to say that I've got the normal ordered product, I introduce some notation. I put 2 dots on either side of the operators. So those 2 dots there indicate that I've normally ordered this collection of operators. And what does normal ordering do? It means that first I write down the daggered operators. So write down all of the daggered operators first. And then second, I write down the undaggered or no daggered operators. Okay? And of course, the way to say it is that first we write down the creation operators, and then we write down the annihilation operators. So for this particular expression, for this normal ordered product of operators that I've got on my page, well, first we write down the creations. So we write down alpha dagger of K2, alpha dagger of K4, and then we write down the undaggered operators. So that would be alpha of K1 and alpha of K3. Now, this is a well-defined prescription. You might be feeling a little nervous because, you know, I didn't tell you the order in which you should write down the creation operators or the annihilation operators. Well, that is completely inconsequential. And why is it inconsequential? What was that? Yes, that's the right answer. It's because the creation operators all commute with each other, and the annihilation operators all commute with each other. Oh, I'm writing the creation again. Let's sort that out. I want an annihilation now. Good. And it really doesn't matter what momenta. Okay, they'll commute with each other for any momenta. So I can swap the alpha K2 dagger and alpha K4 dagger, or I could swap the alpha K1, alpha K3. This is a perfectly well-defined definition. It's a complete definition. And normal ordering is a noun. You can't normal order equations. You can write down certain equations that are true, and you can check that normal ordering them just doesn't make sense anymore. So normal ordering is a noun, not a verb. Let me just give you a simple example. So we know from the harmonic oscillator that A dagger minus A dagger A is equal to 1. Well, that's certainly the case. Now, let's just imagine that we could normal order this equation. Well, if we normal order the equation, so I'm going to interpret that as meaning that now we just normal order both sides. Is the equation still true? Well, A dagger normal ordered is A dagger A. I must put the creations first, minus that second term is already normal ordered. That's another A dagger A. And then, well, 1 is 1. So that doesn't get normal ordered. But A dagger A minus A dagger A is 0. So we get 0 is equal to 1. That's just a rubbish equation. That's just a nonsense. It's rubbish. So the conclusion is you can't normal order equations. And I like to summarize this by saying normal ordering is a noun, not a verb. Okay. Now, let's just relate this back to our discussion of the Hamiltonian. So I told you that the divergence was simply because of an ordering issue. So let's choose a different ordering for the Hamiltonian. Let's normal order the Hamiltonian, okay? Well, if we normal order the Hamiltonian, so what do we have? Well, the half doesn't change. The measure doesn't change. So that's just still an integral d3 over 2 pi cubed. But now if we look at the operators, well, the alpha dagger alpha, the first term, that's great. That is normal ordered. But the second term is an alpha alpha dagger. Well, that's going to swap to become an alpha dagger alpha because that's what normal ordering does. So now if we add those two terms, it'll cancel with the 2 in the denominator, and we land up getting alpha dagger of k, alpha of k. And now there is no divergence. So what I mean by that is, if you were to calculate this vacuum expectation value of the normal ordered Hamiltonian, not only is it not divergent, but it's actually naught. It actually vanishes, okay? Now, you might be feeling a little queasy. You might say, well, which Hamiltonian should I use? Should I use the Hamiltonian or should I use the normal ordered Hamiltonian? Well, remember, they just differ by an ordering, so there is no way to tell. It's your classical expression. In going from your classical expression to your quantum expression, you have to choose an ordering for the different terms. So you'd have to have some additional input. But then apart from that, these two Hamiltonians only differ by adding or subtracting a constant. And if you're going to use this Hamiltonian, for example, to generate the equations of motion, who cares if you added or subtracted a constant? It means that the Heisenberg equation of motion computed using H will be exactly the same as the Heisenberg equation of motion computed using the normal ordered version of H. Great. That basically brings us to the end of this chapter. Let me just make a few quick comments on the exercises.